Okay, so today we're going over section 5.6 and we're going to talk about the fundamental theorem of calculus. And to motivate the fundamental theorem of calculus, how somebody came up with this, let's look at a problem here. The position of a particle that moves along an axis is given by the formula S of t is equal to 4t squared plus 6t. Find the position at time t equals 2, find the position at time t equals 5. How far did the particle travel from time t equals 2 to time t equals 5. These are things you should be able to do. No need to just watch. You should pause the video and do this problem and then move on. Okay. So we're given the position function. First, again, we need to make sure that we're always moving in one direction. And so S prime of t is 8t plus 6. And for positive values of t, if you multiply by 8 and add 6, you're going to get a positive value. Therefore, we're always moving to the right. And so we don't have a problem, right? We don't have to worry about what's going on there. So S of 2, we simply plug in 2 into the formula. We get 4 times 2 squared plus 6 times 2. 16 plus 12. 28. S of 5. Plug in 5 into the formula. 4 times 25 plus 6 times 5. And that's 100 plus 30, 130. Okay, so then at time t equals 2, we were at 28. At time t equals 5, we were 130. How do we find the distance that we traveled from time t equals 2 to time t equals 5? Well, that whole time we were going in one direction. That's important. And so then the distance is 130 minus 28, which is 102. This is probably in feet. But that is the distance. Okay, so what I expect you to get out of this example is if we're always moving in the same direction, so my velocity is always positive, let's say, to keep it simple, then the way I can find the distance that I traveled is just by subtracting the distance at the second time minus the distance at the first time. Okay. So that was simple enough, but let's move on. So the velocity of a particle that moves along an axis is given by the formula v of t is equal to 5. Sketch the graph of the velocity versus time. Find the distance traveled by the particle from time t equals 1 to time t equals 4. What geometric quantity of the velocity graph are you calculating? Okay, so let's make a quick sketch of my velocity function. And so we have t and we have v. And my velocity function is v of t is equal to 5. That's just the horizontal line. And we're only interested in from the time t equals 1 to the time t equals 4. And what you see is that what you are looking at over that time interval is you're just looking at this part of the graph and you're looking at a rectangle, right? Now, what we're looking for again here is find the distance. Find the distance traveled by the particle from time t equals 1 to time t equals 4. Okay, so now the basic formula when you have a constant velocity, which is what you have, is that the distance is equal to the rate times the time, right? So the distance is equal to the rate times the time. There's no need for calculus here. This is just a standard algebra problem. But your rate is 5 and your time is you're going from time t equals 1 to time t equals 4, so 3 seconds go by. 4 minus 1, 3. 3 seconds go by. And 5 times 3 is 15. This is not obvious. But if we go back to the picture that we drew, right, what is the 5 and the 3? Well, this is v equals 5. And so then the 5 is this distance right here. And then the 3 is this distance right here. So then what geometric quantity of the velocity graph are you calculating? So you're calculating the area under this curve, under this velocity function, calculating the area under the function. That was not obvious to me when I first saw it, but that is what we just did. Just found the area under that velocity function. Okay. Now let's solve the problem in a different way. If the velocity function is v of t equals 5, find the position function and use it to calculate the distance traveled from time t equals 1 to time t equals 4. So we know that the velocity is 5. And also what we've gone over is how to go from the velocity to the position. To go from the position to the velocity, we took the derivative. So to start at the velocity and go to the position, we find the antiderivative. And so the antiderivative would have to look like this, 5t plus some constant. And we're not given any information to figure out what that constant is, but it's going to turn out not to matter. Find the position function and use it to calculate the distance traveled from time t equals 1 to time t equals 4. Okay, so again, based on our first example, all we have to do now is find my position at 4 and subtract my position at 1. And so then what we get is 20 plus c minus 5 plus c minus, we got the minus. And then the c's go away and you just get 15. Did not matter what our initial position was, what our position at 0 was. It did not matter what this constant was, because when you subtract your two positions, that constant goes away. And we get the same answer, right? So the answer before we got was 15, and this answer is 15 as well. Right? The velocity of a particle that moves along an axis is given by the formula v of t equals 3t. Sketch the graph of the velocity versus the time. Find the distance traveled by the particle from time t equals 0 to time t equals 6. What geometric quantity of the velocity graph are you calculating? Okay, so again, we are not given the position, we are given the velocity. The difference here from this problem and the previous problem is that the velocity is not constant. So the velocity is this line, v of t is equal to 3t, tv. And you're interested in finding the distance traveled by the particle from time t equals 0 to time t equals 6. So we're going from 0 to 6. Okay, now we cannot use the formula that we used last time. The distance is equal to the rate times the time, because this formula only works for a constant rate, right? And so we don't have a constant rate. So what can we do? Well, this is why the Riemann sums are important. They're going to help you set up problems, and we're going to do a lot of this in 5B, so that's why it's very important that you understand the Riemann sums. Well, what we could do is we could cut this up into even little pieces. During each of those even little pieces, we could put our time into the velocity and assume that over that little time, your velocity is constant, and then we would get the distance would be the area under this rectangle. And then we would do that for each little time interval. And then we would add up all these little areas. But obviously, this area up on top is an overestimate of of how far we went because we have more area. But if you look at this, all you're really trying to do is find the area um, under this curve or under this line. And so then why no need for rectangles because we have a triangle, right? So the triangle, the formula for the area of a triangle is the area is equal to 1/2 the base times the height. The base is the length of the entire interval, which is 6, and the height we get by putting in that 6 into the formula. So that's 18. And so then 3 times 18 is 54. I should have given you units, probably feet, 54 feet. So even though we did not have a constant velocity, we could still use our distance equals rate times time over a little time interval where that then becomes, then we could assume that over that interval the velocity is constant. We can take the right endpoint, the left endpoint, the one in the middle makes absolutely no difference. Then you can see that all you're really trying to do is calculate the area under this. Once you realize that you're calculating the area under this, you can just calculate the area using geometry, formula from geometry. Okay. If the velocity v of t, if the velocity function is v of t equals 3t, find the position function and use it to calculate the distance traveled from time t equals 0 to time t equals 6. Okay, so again, we know that the velocity is equal to 3t. And so then if we're going backwards, we find the antiderivative to find the position. And so then the antiderivative of 3t is 3t squared over 2 plus some constant. Don't know what that constant is, and it turns out it's not going to matter. We can use any constant we want, because now to find my velocity, to find my distance, I'm going to take my position at 6 and subtract my position at 0. And so then when I put in 6 squared is 36. Well, let me just punch that into the calculator. 3 times 36 divided by 2, 54, plus c. That's my position at 6, minus my position at 0, c. Notice again that the c's go away. And so since the c's go away, there's actually no need to put in plus c. I could have just used 0. I could have used any constant, because no matter what constant I use, it's going to go away. So why use any other constant than 0 if it's going to go away? So what we get is 54. The same area, the same. So once you come to terms with the fact that to find your position, to find the distance that you traveled, you're just trying to find the area under the curve, then the distance is going to be the definite integral from where you started, 0, to where you ended, 6, of the velocity function, 3t, dt. And then what we have just seen here is that we can find this area under the curve rather than by using geometry or using something else, by using an antiderivative, in this case the antiderivative of the velocity function, which is the position function, and evaluate it at 6 and subtract what you get when you evaluate your position function at 0. And so anytime we have a definite integral, the physicists said, hey, well, we can look at that as a velocity function. And then to find the definite integral can be just the distance that we've traveled, and then we can just find an antiderivative, and that's where this theorem came from. This is called the fundamental theorem of calculus part 1. If f is continuous on the closed interval AB, and if capital F is any antiderivative, you can use any antiderivative, and remember the only difference between the antiderivatives is just this arbitrary constant. So if we can use any antiderivative, we'll use the one where the constant is 0 because it's going to cancel out anyway. Of f on the interval AB, so if f is continuous on AB and if f is any antiderivative of f on AB, then the definite integral from a to b of f of x dx is the antiderivative of f of b, the antiderivative of f of x minus, evaluated at b minus the antiderivative of little f of x evaluated at a. Okay. So for those of you moving on in math, I'd like to go over the proof. Once you get past your second year of math, it becomes less computational and more theoretical, more proving instead of just computing. And so how you get good at that is by understanding proofs, because later you're going to be asked to do these proofs on your own without just memorizing them, without being told how to do them. And so one way of getting good at that is to start understanding them now. Okay, so we're going to need a couple things. First thing we're going to need is remember that the mean value theorem. And so the mean value theorem was let f be continuous on the closed interval AB and differentiable on the open interval AB. Then there is at least one point C in AB such that f prime of C is equal to f of B minus f of A, all divided by B minus A. So again, this was your slope of the tangent line, this was the slope of your secant line, and over any interval, then the slope of the tangent line is equal to the slope of the secant line for at least one point in that interval. We're going to need to rearrange this. And so if f is an antiderivative of little f, then f prime of x is equal to f of x. So the slope of my tangent line comes from f of x. And the slope of my tangent and the slope of my secant line comes from capital F of x. So then just adjusting this notation, then f of c is the slope of the tangent line, and f of b minus f of a all over b minus a, this is the slope of the secant. So this is the tangent, and this is the secant. But we're not going to need slopes. What's going to be important to us is that then what this tells me is that, remember, if we just multiply both sides of this equation by b minus a, we get f of c times b minus a. And again, f of c is the output at some point, and b minus a is the width of your interval. So really what this is, in the context of what we're doing right now, this is the area under one little rectangle. And what this is telling us right here is that you can find that area, that the area is the same as your antiderivative evaluated at your endpoints, f of b minus f of a. And so all I've done here is just rewritten it. F of b minus f of a is f of c times b minus a. Okay. So now let's move on to the proof. So again, for the Riemann sums, what we did is we partitioned the interval by inserting n numbers, x1, x2, all the way to xn minus 1, be any points in AB such that a is less than x1, which is less than x2, which is less than ... which is less than xn minus 1, which is less than b. Okay, so all we were doing here, again, we're finding the area under the curve from a to b, and then we would put in an x1, we would put in an x2, we would put in, and so on, an x3. And so these values divide AB into n subintervals, a to x1, x1 to x2, ... xn minus 1 to b. Those lengths, as usual, will be denoted by delta x1, delta x2, delta xn. Right? But now using the mean value theorem, on each one of those intervals, the mean value theorem guarantees us that there is some x sub 1 star in the first interval, so that the difference of your antiderivative evaluated at your endpoints, f of x1 minus f of a, will equal this f of x1 star times delta x1. In the second interval, there exists a x sub 2 star, so that f of x2 star times the delta x sub 2 is equal to f of x2 minus f of x1, and so on and so forth, right? And now, when we add all these up on the left, those go away, the x3s will go away, and all that's going to be left is f of b minus f of a. And so by choosing your x sub, so then the one over here will go make that one go away, and they will all go away, and all that's left is f of b minus f of a. So by choosing your x sub I stars as the ones given to you by the mean value theorem, then you are guaranteeing that your Riemann sum looks like the summation from on the right. When you find your Riemann sum, you'll get the summation from k equals 1 to n of f of x sub k, f of x sub k star times delta x sub k. And so then this right here is not changing. So when I take the limit of both sides, and this is the limit as the max delta x as the max delta x goes to 0, on the right you get the definite integral from a to b of f of x dx, and on the left this is not changing. It's a and b were fixed. F of a is an antiderivative, so f of x is an antiderivative, so f of b minus f of a is not changing. And there you go. That's what you were trying to prove. Okay. So just to get you comfortable with some notation, the definite integral from a to b of f of x dx, we're going to need to find an antiderivative capital F, right? And then we're going to need to evaluate it from a to b. And what that means is take f of b and subtract f of a. So this is how I'm going to show my work. This is how the work is typically shown. We don't jump straight to here. We come to here. It just makes things a little bit smoother. Okay, so let's practice this. Find the area under the curve y equals f of x over the stated interval. So again, what gives you the area under the curve is the definite integral. So the definite integral from 1 to 27, and this is x to the negative 23 dx. So this gives us the definite integral. Now with the fundamental theorem of calculus, no need to approximate with rectangles or use rectangles and then take the limit. Now we can just find an antiderivative. This is just a basic power function. We add 1 to the exponent. 3/3 minus 2/3 is 1/3. Multiply by that reciprocal and evaluate it from 1 to 27. X to the 1/3 just means the cube root of 27. So you have 3 times the cube root of 27 minus 3 times the cube root of 1. And that will be cube root of 27 is 3 times 3 is 9 minus 3, which is 6. So the area under this curve is exactly 6. Find the area under the curve, y equals f of x over the stated interval. So 1 over x is just the hyperbola. We're taking the area from 1 to 5. We want to find this area right here. Again, what finds the area is the definite integral. The definite integral from my left limit of integration to my right limit, 5, from 1 to 5 over the interval of f of x, 1 over x dx. Now this is a power function, but the power is -1, and if you add 1 to the exponent, divide by the exponent, you will be getting, you'll be dividing by 0. So no, this is not, you can't use the power function formula. This is the special case when the power is -1. The antiderivative is the natural log. And no need for the absolute value of x because we're only working over the interval from 1 to 5 and all those numbers are positive. So then it's just the natural log of x and we're evaluating it from 1 to 5. When we plug in 1, we get the natural log of 5. I'm sorry, when we plug in 5, we get the natural log of 5. And when we plug in 1, we get the natural log of 1. But the natural log of 1 is 0. So the answer, the exact answer, is the natural log of 5. We can approximate that by punching that into the calculator if you like, but the natural log of 5 is good enough for me. Okay, so again, to evaluate the integrals, you need to be able to find an antiderivative, and so this is so you need to be able to do that. You have memorized what you know how to find the antiderivative of, and you need to know that that's all we have is make what we have match something that's on the table. So this is what we were given, and that is not on the table. We don't have any product rules or quotient rules or anything like that. So all we can do is come over here and rewrite our integrand into some nicer form. So what we can do is use the rules of exponents. This is 1 over x times x to the 1/2. This is then 1 over x to the 3/2. And again, we don't have an antiderivative for 1 over x to the any other power other than 1, right? So we have to rewrite this as a power function, x to the -3/2. So then this becomes the integral from 1 to 4 of x to the -3/2 dx. Now we find that antiderivative by adding 1 to the exponent. 2/2 and -3/2 make -1/2. Multiplying by the reciprocal, -2, and we're going to evaluate this from 1 to 4. I'm going to go ahead and leave this -2 out in front and plug in the 4 and the 1 into that. And so you get 4 to the -1/2 minus 1 to the -1/2. And so then you get -2. 4 to the -1/2 is 1/2. Right, so the -1 means to write your powers in the denominator. The 1/2 means to square root, so the square root of 4 is 2, and the negative makes it go on the bottom, so 1/2. 1 to any power is 1. 1/2 minus 1 is -1/2. And a negative times a positive is a positive. And our area is exactly 1. Now, your answer needs to make sense. Over the interval from 1 to 4, this expression here is always positive. And so then your area must be positive, and that's what we got. If you end up with a negative in this problem, you can have negative answers, but in this problem, since it was always positive, then that would have told you, hey, did something wrong, got to figure it out. Evaluate the integrals using part 1 of the fundamental theorem of calculus. Again, we're finding antiderivatives. You are capable of finding this antiderivative, so you should pause the video and try this on your own and then see what I did. So this is the definite integral from pi over 6 to pi over 2 of this is not, this term right here is not on my table, but you should see that it can be rewritten as 2 times the cosecant squared of x. And dx. By writing it like this, now this is on my table. This is just a power function, so that one we just add 1 to the exponent, x squared over 2, divide by the exponent. The antiderivative of the cosecant squared is the negative cotangent of x. And we're evaluating this from pi over 6 to pi over 2. When you put in pi over 2, you get pi squared over 4 times the 1/2 is pi squared over 8. The cotangent is the cosine over the sine, and the cosine of pi over 2 is 0. So the cotangent of pi over 2 is also 0. And so times 2 is also 0. And then minus, then when you put in the pi over 6, you get pi squared over 36, but then you multiply that times that 2 in the denominator, so pi squared over 72. And then minus, because there's a minus here. Be careful with your minuses, there's 2 terms. So you should have these parentheses here. And the cotangent of pi over 6, 30, 60, 90 triangle, pi over 6 is 30 degrees. This is the 60 degree, this is the 30 degree, and then this was 1, this was 2, this is the square root of 3. The tangent is the opposite over the adjacent, and so then the cotangent is the reciprocal, square root of 3 over 1. And so we combine the like terms, 1/8 minus 1/72. One-ninth. So you get pi squared over 9. And then this minus gets distributed to here. That will make that a plus, square root of 3. And there you go. So let's move on. Okay, so fundamental theorem of calculus requires that we find an antiderivative. The absolute values are not on your table, so you need to be careful with this. So if you want to use the fundamental theorem of calculus, here's what you can do, right? So if we look at y equals 2x minus 4, then the graph of that is a line with a positive slope that crosses the y coordinate over, that crosses the y-axis over here at -4 and goes over here. It crosses the x-axis. 2 times 2 is 4. 4 minus 4 is 0. So it crosses over here at 2, 0. So what this picture tells you is that to the left of 2, this expression 2x minus 4 is negative, and to the right of 2, it's positive. So then what that tells us is that the absolute value of 2x minus 4 can be rewritten as a piecewise defined function. When x is less than 2, we get the opposite, which is negative 2x plus 4. And when x is bigger than 2, then we get the same thing, 2x minus 4 when x is bigger than 2. And so what we can do with this one integral, This is why one of the reasons why we learned one of the theorems from last section. We can break this integral up to go from 0 to 2, and for that, the absolute value of 2x minus 4 becomes negative 2x plus 4 dx. And then we add the area from 2 to 6. And the absolute value of that is just 2x minus 4, because over the interval from 2 to 6, that expression is positive dx. Now these are simple and integrable functions. I'm sorry, these are simple functions that have simple antiderivatives. So this first one would be negative x squared plus 4x, and we're evaluating it from 0 to 2. And this second one is x squared minus 4x, and we're evaluating it from 2 to 6. 0 to 2. When we put in 2, we get negative 4 plus 8. When we put in 0, we get 0. When we put in 6, we get 36 minus 24. And when we put in 2, we get 4 minus 8. Negative 4 plus 8 is 4. 36 minus 24 is 8. I'm sorry, 36 minus 24 is 12. And then 4 minus 8 is negative 4, so minus negative 4 is the same thing as plus 4. 16. And so then we get 20. It's important to have more than one approach, because what we could have done with this problem, even though we now have the fundamental theorem of calculus, is we could have graphed the function. The graph is an angle whose vertex is over here at 2, because that's what makes this 0. 2 times 2 is 4, minus 4 is 0. And this is just a standard absolute value graph. When I put in 0, get absolute value of negative 4, which is 4. And when I put in 6, 2 times 6 is 12, minus 4 is 8. And so then the area of this triangle is the base, 2 times the height 8. I'm sorry, times the height 4. 4 times 2 is 8. Divided by 2 is 4. That's this. And we were finding the first integral found at this area here. So that's where that 4 came from. For the second triangle, the base is 4. The height is 8. 4 times 8 is 32, but then we divide it by, so this was 4. And then for this second triangle, base is 4. Height is 8. 32 divided by 2 is 16. So that's this area right here. And that's this 16. And so then your area is 4 plus 16, which is 20. A lot easier. So just because you have a new tool doesn't mean you have to use it for everything, unless you're told. Unless I say use the fundamental theorem of calculus, then you have to use the fundamental theorem of calculus. But if I just say find this definite integral, this problem, in my opinion, is easier to say, okay, well, I'm just trying to find the area under this curve. This is just 2 triangles. Let me use geometry. Okay. Next, we have the mean value theorem for integrals, right? So if f is continuous on a closed interval a, b, then there is at least one point x star in the interval a, b, such that the definite integral from a to b of f of x dx is equal to f of x star times b minus a. And so what that is really saying is that over an interval, there is exactly 1 point, there's at least 1 point, so that the area under the curve, because that's what the integral from a to b is exactly equal to the area of this one rectangle, right? That's kind of surprising, but it's not obvious, at least it's not to me, but it's kind of cool. Now, doesn't tell you how to find the x star, and it turns out what we really need this for is for this next theorem that's very important. So this just tells us that there is a number in there, so that the area under the curve is equal to the area of this one rectangle, whose height is f of x star, and whose width is the b minus a. This is what we need that for. This is called the fundamental theorem of calculus part 2. Right? So a function is just a rule that assigns to each input only one output, and there's lots of different ways of defining functions. Now that we have a definite integral, here is a way of defining a function. Right? So it turns out that if f is continuous on an interval, then f has an antiderivative on that interval. In particular, if a is any point in the interval, then the function f, defined by f of x equals the definite integral from a to x of f of t dt, is an antiderivative of f. That is, f prime of x is equal to f of x for each x in the interval. Or in alternative notation, the derivative of this function is the function that you started with. So a couple things here. We saw earlier that just because it was continuous did not make it differentiable. So f of x equals the absolute value of x is continuous, and it's not differentiable at 0. The derivative is not defined at 0. What this tells us is that if f is continuous, then f has an antiderivative. So this has an antiderivative. Doesn't have a derivative, but it does have an antiderivative on that interval. And in particular, the way it goes about showing that it has an antiderivative is it shows you how to make the antiderivative. And you make the antiderivative by defining it to be the definite integral from a to your input variable, x. And this is a dummy variable here, f of t dt. We can't have an x here. It has to be a different variable. Otherwise, you wouldn't know where the input variable was. And so this is an antiderivative. Of f, that is f prime of x equals f of x for each x in the interval, or an alternative notation. Okay, so now we have derivatives and antiderivatives, and it should be intuitive to you that they're reverse processes, and this outlines that, this highlights that, right? This tells us that if we take the derivative of this function that we obtain by using the antiderivative, we end up right back where we started. And that shouldn't be surprising. That should be the case because they are reverse processes of each other. Okay, so let's prove it, right? So what we're going to do is, one way of showing that it has an antiderivative is by finding the antiderivative, and they've given us a formula. So when we have a new function, like we have right here, this is our function, and we don't know how to differentiate it, we go back to the definition. And so here's the definition. We want to make sure that if we take the derivative of capital F, we end up at little f. But the definition of the derivative tells us that the derivative is the limit as h goes to 0 of f of x plus h minus f of x all divided by h. Now this h right here, we can factor it out. That's all we've done there. And f of x plus h, we just replace the x with x plus h. F of x, that stays right there. And if you notice, we have an a here and an a down here. And if we could have the a up here, then we could join the two integrals together. So that's all we're doing in going from this step to this step. All we're doing in going from this step to this step is switching the limits of integration. And changing the sign. Instead of from a to x, now it goes from x to a. And what's the point of that? Well, we went over last that we could do that. And now why would we want to do that? Well, because this is now the same as this. So this one goes from x to a, this one goes from a to x plus h. So now we can put them together and have the limit as h goes to 0 of 1 over h times the definite integral from x to x plus h f of t dt. And then this is where the mean value theorem for integrals comes into place, right? So then that means then that so using that theorem, there is an x star in between x and x plus h, so that the limit, so that this definite integral can be replaced with the width of the integral, which is just h, x plus h minus x is just h, times f of x star, and x star is in between x and x plus h. These h's go away, and we're taking the limit as h goes to 0, and so we're some number in between these is getting closer and closer to x, since it has to be between x and x plus h, and h is going to 0. So this is just f of x. And so that shows that that is the derivative. Shouldn't be surprising that if you form reverse processes, then you end up right back where you started, right? And that's all this says. If you integrate and then differentiate, you end up right back where you started. You started at this function, you integrated and then differentiated, and you get right back where you started. Okay, so let's see some examples of that. Problem number 58. Define f of x by f of x is equal to the definite integral from pi over 4 to x of the cosine of 2t dt. So part A, use part 2 of the fundamental theorem of calculus to find the derivative. So part 2 of the fundamental theorem of calculus is just that your derivative will be the original function that you started with. Be careful, this is a t because that was just a dummy variable. This is a function in x, so your input variable needs to be an x, and there you go. Now, part B, we won't always be able to do this, right? So check the result in part A by first integrating and then differentiating. Okay, so then f of x is equal to the definite integral from pi over 4 to x of the cosine of 2t dt. This is a definite integral. So to evaluate this definite integral, I need to come up with an antiderivative for the cosine of 2t. We could do a u substitution, but I'm just going to go ahead and build it. I'm just asking myself, what do I take the derivative of to get the cosine of 2t? Well, to end up with the cosine, I needed to have started with the sine. But the only way I'm going to get this 2t inside is if I started out with the sine of 2t. But if I take the derivative of this, I will get an extra factor of 2. So to fix that, I just divide by 2. You can go through and do use substitutions if you like. I'm not going to. There's an antiderivative. Something as simple as that. We can just guess what the answer is and then check it. The antiderivative of the cosine of 2t, sine of 2t, but the derivative of the sine of 2t is cosine of 2t times 2. We have an extra 2, so just divide by 2 and then fix it. And we're evaluating this from pi over 4 2x. This then becomes the sine of 2x over 2 minus the sine of pi over 2. Pi over 4 times 2 is pi over 2 divided by 2. But the sine of pi over 2 is 0. So when we divide it by 2, we also get 0. And so then this is just the sine of 2x. But now that's f of x. So let me go ahead, and this is now in closed form, nice easy formula, the sine of 2x. And so now f prime of x, it's composition, derivative of the sine is the cosine. Oh, I'm sorry, I forgot the over 2, lost the over 2. This wasn't going to work. Over 2. But now, when I go to take the derivative, we have a constant, which I can ignore. The derivative of the sine is the cosine, same inside, times the derivative of the inside, times 2. And I have this 2 down here that cancels out, and we just end up with the cosine of 2x, which is what I got over here. Okay, so again, we can't always find the antiderivative. So you can use this technique to define a function. When you can't find the antiderivative, then you just leave it in integral form. But you know what the derivative of that function is. It's the original function that you started with. Okay. So again, here, you should try these on your own. But if we're integrating the function 1 over 1 plus the square root of t, and then we're differentiating it, you're going to end up right back where you started. Make sure that you change your variable. And again here, don't know what the antiderivative of the natural log is. But if I'm integrating the natural log and then differentiating, then I'm going to end up right back where I started. Okay, so in this problem, it says let f of x equal the definite integral from the square root of 3 to x of the inverse tangent of t. Find a f of the square root of 3. So to find f of the square root of 3, we just simply go and we replace x with the square root of 3. And even though I can't find an inverse, even though I can't find an antiderivative for the inverse tangent of t, I know this value because these are the same. The answer is 0. For part B, I want to find f prime of the square root of 3. Well, before I find f prime of the square root of 3, I should find f prime of x. So f prime of x, the derivative of this function, is again the function I started with, inverse tangent of x, which then means that f prime of the square root of 3 is the inverse tangent of the square root of 3. And the inverse tangent of the square root of 3 is just asking what angle do you take the tangent of to get the square root of 3. So the square root of 3 is a special ratio, comes from the 30, 60, 90 triangle. This was 60 degrees, this was 30 degrees. This was 1, 2, square root of 3. The tangent is the opposite over the adjacent, and if I want to end up with a square root of 3, then I had to have been looking at the 60-degree angle, pi over 3. And part C is just asking for f double prime of the square root of 3. Well, before I find f double prime of the square root of 3, I should find f double prime of x. Well, I know what f prime of x is. the inverse tangent of x. And so then the double prime is just the derivative of that, which is 1 over 1 plus x squared. And so now if I'm going to substitute in the square root of 3, I get 1 over 1 plus 3, which is 1/4. And there we go. Here's your homework for this section. This will be due on the 30th of April next week. Have a good day. Thank you.